No, good afternoon. I don't know what time is it. Good afternoon, everybody. So welcome to this tutorial on AI and machine learning for data communication networks. Before starting, just some small notes. I sent you in the chat, actually, for those students that would like to have a certificate of participation. There is a Google form that you need to fill in. So please go there to the link. So you see there in the chat, just go there and you fill in the information, and you will get by email the certificate. Okay, so just don't forget to do it, because if you don't do it, then yeah.
Sorry, please can you resend the Google form link? Because yeah.
I will, maybe you don't see the link. Okay, I can resend it. Let's see again. There. Okay, great, good. So yeah, don't forget that part. About the slides. Actually, the slides are online. They are not linked to the tutorial page. There will be a link afterwards, but actually they are at my personal web page. So maybe if you go, yeah, I think you can see them directly at. I think they are there. Slash, and there is a pointer to AI4NETS slides. Yes. So I send you here, there is this link. So if you click on that link, that is actually my personal website. It goes directly to that basically entry where you have the slides of the tutorial. Actually, I mean, before even starting, there are 5 slide sets there. These slide sets are actually part of a course that I normally give, that it's a 1-week course. So of course, today we will just go through parts of this. But yeah, I mean, you have them there. I didn't want to put the slides anywhere else because I periodically update them. So from time to time there, I will be hanging, let's say, the latest versions. Okay, so but basically we will go through the introduction. We will skip the part of shallow learning. We will go a bit into deep learning for those that are more new into the topic. We will not go through the big data tooling part, but I will just do some mentions because it's also very important when you need to work with machine learning, you will face big data. And then I will just do some kind of skimming through other learning topics that I think are very interesting. Some of them are not so new, and some others are more like hot topics. And yeah, I mean, so that you have an overall idea of what's currently the space. Just know that everything I will show you, let's say everything that is related to learning, it's a huge space. So of course there are many things that I will not be touching, and there is much more that I have no experience at all. So yeah, I mean, if you are completely new to the space, don't think that what we are going to discuss today is the full space of AI and machine learning. Okay? So basically, the full tutorial is 3 hours. So what I propose you is, let's see if we can make the 3 hours. Maybe at some point we say that is a bit too much, but I will try to do 3 blocks of more or less 1 hour, and that we can have 5-minute breaks in between. So let's say we take a break at 5 and a break at 6. And yeah, the other thing is I have the chat open. So if you have questions, I mean, feel free just to put them there, and yeah, let's try to make it a bit interactive. Yeah, because I know it's a bit boring to follow so many hours of talking. Okay. Okay. No, you don't see. I just realized that you don't see. Yeah, of course, you just see the main screen. Okay. So first, I will before starting the whole thing, I will just introduce myself. So my name is Pedro Casas. I am senior scientist in the AIT Austrian Institute of Technology. I'm based here in Vienna, Austria. And I basically work in a competence unit that it's called Data Science and Artificial Intelligence, where basically what we do is we try to solve problems where we have data and we can apply automation for the analysis and getting information out of that. But my background is much more on communication networks. So this is what I will be showing. A small maybe recap on my path to how am I into this AI for networks. I think that nowadays it's clear that, yeah, most of us are trying to somehow do something with machine learning. And yeah, I mean, makes sense because there is lots of data, computational power, and so on. But I started, let's say, something like 15, 17 years ago when I'm original from South America, from Uruguay. And there, when I was becoming an engineer, I discovered something very interesting that were some models of neural networks that are called random neural networks. And I was working on something that I'm still working today, that it's quality of experience prediction. So from there, at that point, I moved to France for doing a PhD in computer science at Telecom Bretagne. Basically, there I was working on data analytics for anomaly detection and traffic engineering. Then I was doing my postdoc at LAS CNRS in Toulouse, working on unsupervised learning for security. And then finally, yeah, I decided to come to Austria, complete adventure. Was not very sure about coming to Vienna, and at the end of the day, yeah, it's a very interesting country, very nice city, and I welcome you all coming here. And I started my path in senior research in a center that it's called FTW. It was a center for research in telecommunications, and I was working on traffic monitoring and analysis. And since, let's say, already 4 or 5 years, I came to the AIT Austrian Institute of Technology, and I'm working on AI/ML for monitoring and analysis. I have 2 daughters. Actually, this is what I always try to say. I am full-time daddy, and in my free time, I try to do some research, some work. So my 2 daughters, they are 6 and 4. They look, let's say, very happy, lovely, but trust me, and now these days we be a nightmare. I guess many of you are in the same situation. Luckily now, the new lockdowns are not closed in the elementary schools and the kindergartens. So yeah, that's basically me. In AIT in the data science field. So here actually we work in a center that's a center for digital safety and security. So the things that we try to do linking data science are more based on security. So we have like 3 big areas. One is about 5G secure networks. Another area that it's, let's say, very, very interesting is about quantum communication networks. And there we're trying to go into fields now, a bit more hot topics like quantum AI and these type of things. And then, yeah, what I was saying about data science. And within the data science, the AI4NETS, it's more a mix of the part of applied artificial intelligence. So we are not here developing, we don't develop new machine learning or AI algorithms, but we basically try to apply them and tailor to the different use cases that we have to face. And the field of AI4NETS is basically a mix of applied machine learning, or let's say, sorry, I will be abusing a little bit of the term AI. So basically everything I will be showing you will be much more machine learning. But yeah, I mean, nowadays we are all of us abusing a bit of the term artificial intelligence. And in some cases, what we do, it's in the border. So I will be talking about AI, ML without making a distinction. So the other branch that is part of AI4NETS, it's scalable data analytics. And you will see that when we are doing applied machine learning, and when you do machine learning, you will be dealing with big data and with, let's say, lots of data. And in order to do things that really work in the practice, you will have to smash big numbers. And to do that, you will need to more or less understand about big data tools. So there is one slide set that I try to go through these concepts. We will not see it today, but yeah, it's there. So you can see from things like Spark to things that are much more deep learning, like going through TensorFlow, PyTorch, and these type of frameworks. Just a clarification, if you are new to deep learning or you are jumping into this, I deeply recommend that if you have to choose a framework, go for PyTorch. From an experimental point of view, at least, it's much more flexible and it's really, let's say, much more for researchers. If you are going for more commercial solutions or things that you want to deploy, of course, TensorFlow, it's I would say much better in that direction. So I do some comparisons there in the slides. But yeah, I mean, remember in TensorFlow you have Keras now integrated, so it's actually now it's much easier, much easier to integrate and to do your models in TensorFlow as well. So yeah, just last thing about AIT, we are about 1,300 people working in different research domains. And the center where I'm working, we are about 300 people. So let's go, now that I did an introduction of myself, let's go to the topic. So we all know that AI has produced major breakthroughs in the current data-driven landscape. So we see this in everything that it's image processing, natural language processing, self-driving cars, systems, a lot of different domains that are very, let's say, known to the standard people, to everybody. But when it comes to data communication networks, I would say that, of course, we are doing many things and there are many, let's say, solutions that we are using. But I would say that overall, we are not seeing the same level of success as we see in these other domains that I'm telling. So I really think that the application of machine learning AI in communication networks is still at a very early stage, which means that for us means, let's say, a very fertile field to dig into. But the thing is, okay, why would someone like to do machine learning in communication networks? What I will be showing you here, of course, there are many reasons why doing these things. What I'm showing you here is much more the perspective from network monitoring point of view, that it's basically my field. What I try to do is to passively analyze the data that I see collected in the networks. And basically, if we just think on the overall picture about the reliance that we have on the internet, we can say that our full reliance on the internet today makes us victims of the success of the internet. So we are fully connected, everything is online and so on, but we are very vulnerable to the shortcomings that the internet can have. And so the internet itself, it's a very complex system that if we want to understand how it works, we want to monitor and we want to detect issues, anomalies, attacks, and so on, it becomes quite difficult to do it in a kind of traditional, I would say, more modeling approach of systems, because the reality is that, yeah, the internet today is a bit tangled. So if you consider here, I have a picture of what was meant to be a traditional internet-like network, where it was a kind of very structured network with different type of, let's say, levels for autonomous systems and so on. But of course, the internet today, I would say, serves for mainly two, let's say, big applications. One is to basically feed contents to the end users. So today we can talk about the Internet of Contents, where basically we have all these hyper giants, large content providers that are basically modifying the architecture of the internet itself. If you see today, the internet is much more flat, because of course there are not so many clear distinctions between certain ISs, content providers, and so on. And the other big, let's say, application of the overall internet is to connect our critical infrastructures. So one of the things that is happening today, and is happening in the last years, is that now we are trying to automate as much as possible everything we can. And this means that we need to use communication networks to connect systems that can be remotely, let's say, managed and so on. And when it comes to critical infrastructures, here I'm talking about energy systems, I'm talking about financial systems, I'm talking about, let's say, transport and so on. We are seeing a move that is going much more into using internet itself to connect these type of networks. And so this is actually making the whole picture a bit complicated, because imagine that now we are having a communication network that wants to provide things that are highly reliable, and at the end of the day, it's actually a very complex end-to-end system to handle. This is a very interesting picture. I don't know if you know this internet mapping project. It's a funny thing where basically people can say, what do you think the internet is about? And this is basically the picture that one very expert person did about what the internet looks like. And it's exactly this. It's a big complex system. It's a tangle that, even though you might understand the protocols and the things, how they work, when you put them together, it's very difficult to understand what's going on there. And so, just to conclude from this part, is that the complexity of, in general, large-scale networks requires that we use much more, let's say, advanced analytics to understand what's going on in order to match the expectations that we want from the network, especially in terms of security, robustness, performance, and adaptability. So adaptability in the sense that if you think one of the major things that is also driven the AI4NETS space, it's everything that is SDN, NFV, virtualization, and now the power that we have just by software to reconfigure networks and to, let's say, adapt them on the fly. So for doing all this is that basically I see that the AI4NETS, it's, let's say, coming into place very strongly. Okay, so this is more about, okay, what the internet is I would say, a complex system. When we want to do AI4NETS, the overall idea is to have a kind of radical change in the way we manage communication networks. And the idea is to say, today when you have a complex system, whatever this complex system can be, the complex system could be, let's say, natural language processing. A complex system could be just, let's say, translation of languages, or could be, let's say, automatic writing. If you are talking about image, could be automatic image recognition and so on. We are relying more and more in data to explain those complex systems, and on automation of algorithms to analyze and get some things out of there. So we want to do the same things for the internet or for the networks. What we want to do actually is to turn the internet or networks in general into something that is fully transparent, and this concept of liquidity. It's something that actually can adapt to the needs of the end applications, and that basically we will not have to care about them for things like security, or when there are anomalies to be, let's say, self-auto-configured and so on. And yeah, this is, let's say, the overall picture of what do we want to do in AI4NETs. But of course, if you think about this path, it's not new. I mean, we are talking about this type of automatic, self-driven networks, cognitive networking, and so on for the last, I would say, 20 years. So in 1998, there were these initial concepts of cognitive networking, in which the idea was thinking about networks that will have cognitive capabilities and could, let's say, take measurements and learn things from them to react in the future and so on. Since then, of course, we have seen many terms refurbished, like self-organized networks, self-aware networks, self-driving networks, intelligent networks, all the names that you would like to have. But there is a striking gap we see, and the actual deployment of AI-based systems in operational environments. Let's say, to tell the truth, there are many different, let's say, complexities that make it a bit more challenging to just grab AI-based solutions and deploy in the network and fully trust them and say, okay, now we can use it to automate the networks. What we can do is to try to improve parts of the networks and improve specific applications by using AI. What I will try to do in the next slides is to go through some of these complex challenges that are associated. I mean, some of them, of course, are challenges linked to AI and machine learning, so general challenges of doing a data-driven analysis. But let's say, I think that the specific field of networking exacerbates some of these challenges because of the complexities that are there involved. Nevertheless, you know that the ideas of turning networks into self-driving components, it's a very hot topic. And this is a very hot topic not only for ISPs and network, let's say, the operators themselves, but the vendors. Of course, all the vendors, they are selling appliances that you want them to self-configure. And the self-configuration could be, let's say, at different parts of the network. Imagine, for example, when you are deploying a new radio network, if you want to deploy now 5G, it's not trivial to do things from the, let's say, from the planning point of view to the configuration of the network itself. Imagine that the number of parameters to configure when you deploy a new network to actually achieve the best performance that you can, avoid interference and so on, can be really a complex, nasty problem. And there we are seeing that we are trying to do more and more of AI4NETs, but also the content providers are trying to use this type of technology to improve their own business. So the whole internet business for content providers is about keeping the user engagement. So from simple applications that are mostly based on recommendation systems and so on, that basically, Netflix, Amazon, whenever you're there, they want to keep you there so they can sell you more advertisement and so on. Okay, in all of these situations, the idea of AI ML for nets applies. So today, if we take a look at this kind of path to full autonomy, I think that we are still, of course, we have achieved quite some developments, leaving fully human-driven automation. So, of course, we have lots of things that are running independently of having direct human control, and this is very good. But we are still very far from the full autonomy, and actually, there is a big plan to go into full autonomy networks in about 5 years. I don't think this is much feasible, but yeah, just to tell you that there is a very strong interest into this. In my case, when I talk about AI4NETs, I have 4 specific domains that I work in. As I was saying, security, monitoring and analysis, detection and diagnosis of anomalies, and internet quality of experience. So this is basically the last element. It's about monitoring networks so that they can fulfill the requirements of the applications that the end users are actually having. And the interesting thing about AI4NETs, it's a meeting point of, let's say, different fields that are complex. So of course you have everything that is, I would say, big data, or let's say, if we consider the big data paradigm, AI4NETs involve all the major learning and big data challenges that we have there. That it's our, let's resume it to the famous 4 Vs that you had in big data. So in communication networks, we have massive volumes of complex and heterogeneous data. When I say complex and heterogeneous, is that, of course, in a network, depending on the vantage point and the type of protocol you are monitoring and the type of data and mix of traffic and so on that you're monitoring, you can have very different things. So in image processing, you might have, okay, images that are from nature, images that are synthetic, but things that tend to be more similar in between these categories. In communication networks could be whatever. So imagine now that we also have machine-to-machine communications, IoT, different type of services communicating there, could be very complex. And at the same time, about the volumes, right? We are dealing with massive volumes of data. Just think about opening one vantage point in a kind of aggregation point in a core network and let it capture data for, let's say, a couple of minutes. You will have many terabytes of data ready to analyze. So again, it's a super challenging problem in the sense that how do we deal with these volumes of data and this variety? The other major complication that it's added by networks, it's about the velocity. So velocity of data, of course, talks about dealing with dynamic streams of data. So I will be talking a little bit about this, but when you are doing machine learning, you can either think that you have all the data already in your hand, and you will do a kind of offline analysis of all this. But in many applications, of course, the data, you don't fully have it, but this data is something that is coming continuously. So let's think about networks, and it might be coming very fast. So this kind of fast and high dynamic environments that we have in networking makes the whole learning applications much more complicated. The other thing that is very challenging for us is the lack of ground truth. So of course, we will see that in machine learning, we can do many things that are, let's say, unsupervised or at least semi-supervised. But I would say still 90% of the things that we do at the AI ML space, it's based on the availability of ground truth, of having, let's say, labels for the things that we want to learn. And when we are dealing with networking problems in the wild, this is actually not the case. It's very difficult for us to have ground truth. So this adds more complexity to the overall picture. So what I'm saying is that if we manage to conquer the AI4NETs problem in networks in the practice, then this type of learnings that we will get from there would be able to let's say, be applied in many other fields. So, of course, here I have some examples about, I know, IoT, Industry 4.0, scalable computing, trading, and so on. But solving these different problems for our field opens the door to many things that actually could be beneficial for the all AI community. Okay, this is more about the things that I'm doing, but one of the things now that I was talking about the AI community is that in general, in the networking field, we don't have, we are not very attractive for the AI and machine learning communities. So if you go to, let's say, the top conferences today about machine learning, artificial intelligence, so NeurIPS, ICLR, ICML, and so on, there is barely no one doing anything about networking data. So there are many explanations for this. Of course, one of the things is that for most of the people, the internet or the networks are things that are just there and they work fine. So you don't have so many use cases that are interesting to tackle there, which of course is partially true. But yeah, I mean, there is some truth on this. But at the end of the day, when we are dealing with AI4NETs, you will see that it's mostly people that we have, that we try to acquire expert intelligence to try to solve this. And hey, you know, instead of having this type of image processing solution, we want to have this type of packet traffic processing solution. And yeah, this is actually limiting the speed that we can actually improve on this type of direction. AI and machine learning, it's not everything so bright. And we are seeing this more and more often about the challenges and the limitations, I would say, of dealing with everything in a kind of data-driven approach. So if you think about science in general, of course, depends a lot on the field, but in the past, everything was about trying to model systems, right? So whenever you wanted to explain something, you want, I mean, recall all these, you remember Q-in theory, Erlang formulas, when we wanted to model, let's say, call centers, blocking probabilities, and so on. We always try to do a mathematical model that describes our, let's say, interpretation of the reality. And based on that, we want to do analytics. But the temptation today is that many systems that are very complex are not very easy, or let's say in some cases, if it's a complex system, you cannot even model it. So the way to characterize and to do things on that today, given that we have so many data, is to do it in a data-driven approach. You just have a system where you have data inputs and data outputs, and you try to understand what's going on there, treating the system as a kind of black box. Of course, the improvements in availability of data, the improvements on computational capacity that we have today, and the improvements in algorithms of machine learning, so in particular deep learning, have turned all this kind of data-driven analysis of complex systems into kind of default approach to doing things. But of course, there is a big problem here, and it's what I call the Achilles heel of machine learning and AI, that it's about bias. So bias is everything that actually can, let's say, make our whole analysis based on data-driven or based on machine learning algorithms fail. So probably you know this image of a complex system. So this is, some people, they call it the elephant paradox. So basically, if we assume in this picture that the elephant it's a complex system, and that all the researchers that are trying to analyze it are just having access to part of the thing, what we see here is that, okay, the data that the people is analyzing is biased. What does it mean that it's biased? Is that the data that we have describing a complex system can be partial, can be just showing a small part of the reality of the complex system, or could be, let's say, modified by some reason, even by some problems, or could be intentionally modified, such that the data itself is not really reflecting the reality of the problem. But not only the data, if we think here in this example, the different researchers or the models, the machine learning models that we are using, they are also biased. And why is that? Because each machine learning model, you can think about that as a kind of filter. And it's a kind of filter that has its own properties, its own assumptions or hypotheses of behavior of the analysis that it has to do. It has specific mathematical properties. Sometimes these models, they are very complex and they lack transparency. Imagine that we rely all our understanding of these complex systems on the data. Is also as users. Sorry? There was a question? No, sorry. So what I was saying is that at the end of the day, we can end up, let's say, being biased as end users, or let's say be completely unaware of the limitations of machine learning. And this brings us to things like whenever we build a new AI or machine learning model, it's very difficult, or in general, there is a whole field about how to evaluate and test the models, how to certify that these actually models are working properly and correctly as they should. Some of the things that come very often in making mistakes with AI and machine learning, it's about mixing up things like correlation and causality. Many times things that we see are just plain correlations about phenomena that we have in the data, but are not linked to causality. It's not that one thing is happening because some other thing happened. So most of the machine learning approaches that we use, they don't consider causality in the whole analysis. And so we can take completely wrong assumptions in saying, okay, this is happening because this and this has happened before. So just to be aware that, of course, we want to go into this direction because doing things data-driven, as I was saying, can be very helpful when we are not able to understand and model what we are doing. But yeah, we have to be aware of the limitations of all this tooling. So let's go now onto some elaboration of what I think are some of the blocking points of machine learning in networking. So, I mean, it's basically part of the things that I have been mentioning to you. So let's put the chat here. But yeah, I will try to elaborate on some of these showstoppers to just for you to have it into account to say, okay, next time when I will be working on this, let's try to consider these different problems. So one of the things that I was talking is about complexity of the data. As I was saying before, when we talk about large-scale networks, the data that we are analyzing is quite complex. And if you just assume a comparison, I will try to do comparisons to more, let's say, standard problems where AI is providing lots of success. So if you think about doing a face recognition or let's say image processing, the complexity of the data, I would say it's quite uniform in the sense that all faces, imagine that you want to detect faces, faces are similar all over the world. So in general, a face to us has two eyes, has a nose, and yeah, I mean, even though of course faces are completely different in different countries and so on, the main structure is more or less similar. So from that point of view, it wouldn't be that crazy, or we shouldn't be so much surprised that doing face recognition is not actually that difficult in the practice, right? That you can train one model to detect faces using a significantly big amount of data, and that then this system you deployed and will work quite well in every situation. But imagine that tomorrow I start having faces like this one. Imagine that tomorrow we start having faces that are not the traditional face, but are things that are, let's say, changing completely from what I saw at the training time. Are the things that happens to us in networking, because in networking, the things change very fast. And actually, when we are dealing with the data, the complexity makes it, let's say, more difficult to handle into these type of generalization problems. So I think that here, to start with, we are dealing, in my perspective, with much more complex data than in other traditional fields. As I was saying about the diversity of the data, this is also linked to the complexity before, but But yeah, I mean, it's very different the type of data that you can have in different parts of or in different networks because of, let's say, the data that flows through a specific network, say, the many specifics of that network. So imagine if I want to learn some models to do traffic classification, when I want to learn some models for doing detection of attacks, it will definitely be different what I can learn in an ISP network in Uruguay, where the traffic mix is one type and where the type of attacks could be of some nature and the architectures themselves can be of nature whatever, to something that I can then apply into an ISP, let's say in France, because maybe there things are completely different. So for us, this kind of diversity of the network data says that, okay, depending where do I learn and where do I apply the model, the whole thing can really fail. So it's something very difficult to say, okay, I can learn from aggregation of data at the customer IP networks, at the ISP networks, at the IXP points of exchange points, and so on. And yeah, I mean, this makes also the thing much more complex, right? Because it depends on where you learn, where you can apply. Regarding dynamics, okay, this is exactly what I was saying at the very beginning. Data dynamics in networking, it's let's say it's by default the normality. So networking data is in general non-stationary. Of course, you have to go to higher aggregations of data to find stationarity on the data. But in general, depending on the different kind of process you want to analyze, it's something that is highly dynamic. And as I was saying, data in networking comes in the form of data streams. So it's in general not something that we have it fully in one disk and we analyze it. But if we want, especially to go into practice, you will have to analyze things that are coming on the fly. In these kind of situations, we can face one of the killing bullets for machine learning, that is concept drift. So concept drift is basically that you learn into some kind of, let's say, context where the statistical properties of your data are certain, but then when you go to apply these models, the statistic characteristics of the data have changed. Even if you're applying in the same place, could be that just because of the dynamics of the data, the things that you learn are no longer valid. And this is something that really it's a complication for us. If you go for image processing, actually, I like to have this analogy for recognizing faces a long time. And this is a kind of interesting application that you want to see if you can recognize faces all over the quite some limitations, of course, because there are changes, there are modifications in the faces, especially linked to tattoos, things that are not that, I would say, normal and so on. Data in general in these other fields is much more stable in time. Whereas in our case, we see that the variability, dynamics, and non-stationarity will make things much more complex. So for example, for us, when it comes to deploying a machine learning system, it's to a solution that will not need to be retrained every a couple of whatever, every a couple of weeks, every a couple of days, every a couple of months. Our systems will need to be retrained. So for us, taking into account things like dynamic learning, taking into account things like more reinforcement learning and these type of paradigms would make much more sense than just plain offline learning and applied. As I was saying, the lack of ground truth. So in the wild, networking data has no labels. So imagine you're capturing data. Yeah, you will not have the labels saying, okay, you know, these flows actually correspond to this application, or these flows actually correspond to this type of attack, and actually this traffic mix actually correspond to traffic that was flowing when there was this anomaly at this node B interface, and so on. It's something that for us is completely unknown. So because of that, everything that is more supervised learning becomes much more challenging. Linked to this lack of ground truth is that we don't have standardized and representative data sets where we can all together work and compare our solutions. So you know that in image processing, there is special attention in reproducibility of research. So there are like open public databases that are very much, let's say, established and recognized. ImageNet is one clear example. Whenever you want to provide a new kind of solution based on let's say, AI, ML, you just test it on image, and there you are sure that you can compare yourself or you can benchmark your solution to everything that has been tested on ImageNet because it's the same data and the same type of labels. So it's kind of easy to compare and see how to advance and how you are improving. But it's very difficult for us. We don't have any kind of ImageNet in networking. We have had in the past different, let's say, initiatives to try to have this, but yeah, it's something that it's kind of difficult. Also because ImageNet is a database where you have labeling, and in our case, we cannot. It's very difficult to label big data because, as I was saying, no interpretation of our data is complex. If you have to do it through humans with domain experts, it's very costly, and yeah, it cannot really scale. Yeah, at large numbers. Another interesting problem for us is the lack of interpretability. This is something that I will be talking next. But in general, when we are talking about machine learning, and especially when we talk about more complex models, in general, let's say these complex models are black boxes. So it's very difficult to understand in many cases when you have these very deep architectures to understand the particularities of the model and why things are happening. So this kind of lack of interpretability makes it sometimes to say, okay, I have this kind of black box model that is performing or is giving very good performance, but I'm not really sure if the model is working as it should. When it comes to image processing, you can say, okay, I might try to understand the things because me as a human, I can interpret what are the different images that I am processing, right? So for example, there is a whole field that it's called explainable AI, in which basically you try to, given a complex model, you try to simplify it so that you can say, okay, you know, this, let's say a system recognizing, okay, in this example, it's a image recognition system that classifies animals. So you have a system and the system is telling you there is a picture of an animal, and the system tells you, okay, this is a cat, and it tells you this is a cat because it has fur, it has whiskers, and it has claws. So for you as a human, you know, okay, this makes sense. This is a cat. A cat normally has these three things. So I could say that this decision that the model is taking, it's coherent. So it makes sense. This model, even though it's very complex, is providing something that is coherent to what I'm doing. But if you try to apply, let's say, something like explainability to a security system that is trying to detect, let's say, malware, what will happen is that malware sometimes it's detected because there are some kind of byte obfuscation in some part of the bytecode or some kind of specific behavior, and you would get something like saying, okay, you know, this flow actually corresponds to a malware because this byte is actually set to 0 and this byte is set actually to 1 and this and that. It's much more difficult for us, even for experts, to even understand if this makes sense at all or not. So even if we will see something about explainable AI, in the case of networking, explainable AI becomes even much more challenging. So again, the problem here is that if we cannot, let's say, explain how the models work, we cannot trust them. And if we cannot trust the models, it's very difficult to deploy them in the practice, right? Because especially for things that could be more critical, like security, self-configuration of networks, and so on, we want to be sure that the things will actually perform as expected. Other thing that actually happens to us is the learning in adversarial settings. So the learning in adversarial settings is that, as I was saying before, many times the data that we are learning on is biased. But many times this bias is not just because we don't know that maybe we were monitoring something that was particular, but also in many cases, there are bias in the sense of data that has intentional modifications within the data that wants to try to fool us. So for example, when it comes to doing machine learning for network security, it happens quite a lot that the data that we try to learn, it's sometimes difficult to understand if it's fully free of attacks, because some attacks, what they try to do is to obfuscate and to actually go undetected through the eye of the expert. And then we would be doing something like learning on top of data that we believe is normal data, but actually could be containing type of attacks and so on. But this happens not only for attacks. So imagine things like, you remember, for example, services like Skype. Skype at the initial times, it was, let's say, a huge threat to ISPs, to the traditional calls business. So whenever the ISP was detecting Skype calls, I'm not saying all of them, but in many cases, they were starting to drop packets just to say, okay, the Skype call will become very bad quality and the user will drop it. So Skype, what it started to do is to basically to avoid being detected. So again, here, I mean, we can say similar things about Quick. There are different things that Quick to operate and so on. So all in all, sometimes we're trying to learn that the main problem we have in networking is that hey, we okay big data and so on, but if we want to pass this into, let's say, deployable solutions, they have to be generalizable. They have to be able to run in different environments and so on. And this is actually one of the, I would say, the main blocking points for this kind of autonomous. Full autonomous network. So yeah, so all of this panorama that I'm building AI4NETs, why I think that the AI4NETs is highly complex and which are the different challenges that we have to face. But I mean, some people, they say when I introduce this part is that I'm very pessimistic about the future of these things, and not at all. Please don't take what I'm saying as a pessimistic way. It's just to say there are many challenges for us ahead, but this makes it actually much more interesting to actually dive into AI4NETs to solve these problems. So what I will be doing now is to okay, checking if there were some questions in the chat. Before going into, or maybe we can do a first break now because it's almost 5. Because what I would like to do then is the following. Here I have some more concrete applications where I will show you some, let's say, applications where we try to overcome some of the different complexities I have shown you before. For example, about explainable AI or how to do deep learning or things like combining models or doing adaptive stream learning. And then I will start going a bit more into detail into some things that are much more for the part of learning itself. Okay? So before going into a small break of 5 minutes, do you have questions, comments, things that you would like to share with all of us? I mean, I don't know if I have to, maybe I have to unmute you.
Yes, I have one question.
Yes.
Skype and the packets, I didn't get what was really happening.
Okay. Adversarial settings is that sometimes when you are trying to learn, you will assume that the data you have, it's let's say what you believe it is. For example, if you want to do imagine that I want to do a system that detects Skype calls, right? In the past, Skype was trying to obfuscate. So basically, Skype was trying to change the way the application was behaving so that when you were monitoring the flows, it was very difficult to say, okay, you know, this flow belongs to Skype or this flow belongs to another application. So in that case, given that it's actually difficult to even for an expert to try to make this differentiation, you might end up with a data set where you have the data that corresponds to the non-Skype traffic that it's contaminated with Skype traffic. So then you will learn a model to detect Skype, and actually in the practice, it will not work because the model will have a hard time to detect Skype versus other traffic because Skype was also present in the other traffic. This happens maybe also for attacks. It happens quite a lot in the sense that sometimes you want to build a model to detect attacks and you're capturing data, but in the data itself that you are trying to, or you assume that is the anomaly-free or attacks-free data, there are attacks hidden. So if there are attacks hidden in that data and you will use it to learn your models, the bias will kill your application because, of course, you will be learning what will be like a normal operation profile that will be contaminated with attacks.
Yes, thank you.
Okay.
So nowadays, most of this traffic on internet, right? Because of this, all our payload is encrypted. So because of that, is it possible to do even like any of the flow detection and do manipulation of this data? Like for a like a middle box, everything looks like a encrypted traffic, right? Is it possible to like how much bottleneck it is?
Sorry, I didn't get fully. I mean, you're talking about the problems that if data is encrypted and
Yes.
it's encrypted to do this type of applications.
Yes, like even to detect detection or even to flow classification or traffic management.
If you think about that's a good question. Actually, this is one of the things that it's, let's say, from the pure networking perspective, everything is becoming end-to-end encrypted. So for us, it's even much more challenging to understand the ground truth, right? Because you cannot go into the payload, so it's really difficult to say. Normally, what happens today, or there are, if you see different papers that they work with encrypted traffic, what you actually try to do there is to learn patterns or learn features that you can, let's say, extract from the encrypted traffic itself so that you can map those features to the different, let's say, attacks or applications that are generating them. Of course, this becomes very complex because, let's say, a very simple scenario was like some papers that they were trying to monitor quality of experience in YouTube traffic. So YouTube traffic becomes end-to-end encrypted, so you can no longer get into the traffic to understand, okay, if there are buffer overruns coming and so on because of the data itself. And what they were doing basically is like you generate your data in some kind of controlled environment using the encryption that comes by default. And based on that, you try to derive some features that will be generalizable and that you can then map those features to, let's say, the specific levels of quality that your YouTube video can have. Of course, it depends because depending on what those features they can be something completely failing. Because if those features are something that are modified by the type of encryption you are using, just like order of bytes and so on, then of course your whole system will fail because then you go somewhere else with a different encryption and that's it. But yeah, I mean, still what is important to retain is that even though you do end-to-end encryption of something, the patterns that are generated at the application layer, right? Like whatever type of application, attack or whatever that generates some pattern, even though the traffic on the lower layers gets encrypted, there will be a manifestation of that pattern into the traffic. So as far as I would say that the main problem here is to get the data so that you can build the features so that you can run your models. And yeah, that's a completely complex problem to deal with. Let's say here in some of the applications I will be talking about encrypted traffic. And yeah, I mean, normally, just to say, what we try to do normally with encryption is just to say, okay, I will assume that I cannot access the payload. So for me, one packet, in order to also avoid the order of the bytes or whatever, I might assume that a packet is just a packet size and a packet time, these type of indications. Then, of course, when you go into the byte code or into the bytes of the packet, yeah, you might try to learn some things and will, in some cases, not be, let's say, reproducible in other encryption schemes and so on. But there is not much more than you can do there.
And another problem is like if it is a strong encryption mechanism, right, it is supposed to not reveal anything. Like we are trying to extract some pattern that is possible if it's a weak encryption. If it is indeed a strong encryption, then I mean no hope of getting any patterns there, right? Unless that is of a particular flow and only headers reveal something which goes as unencrypted.
Yeah, I mean, if you do it in the wild, of course, you will need something that tells you actually what's going on there. If everything is encrypted, yeah, it's and in addition, if everything is encrypted and you are in the middle, then you see nothing. So that's really the worst case. Everything could be encrypted, but if you are close to an endpoint, you can get some sort of ground truth and so on. But yeah, totally agreed. This is something that we are facing more and more. I mean, if you consider the traditional applications for, let's say, ISPs or even vendors that were sitting more on the middle of the network, many of these things now are becoming more difficult, for sure.
Right.
Question.
Yes.
Yeah. Do you try working with, do you try obtaining a synthetic ground truth by running benchmarks to see what a particular reference workload might look like, or a particular reference traffic pattern might look like, so you can make some kind of inference about the traffic that you have, about the mix of traffic that you might have, understanding the deviations and so on?
Yeah, I mean, it's a very good question. And let's say, if you think about what we were doing in the past, we were trying to model some systems. For example, again, I go to YouTube. We were trying to model how YouTube traffic was behaving so that then I can use that model to generate traffic and then try to generate, let's say, mixes of data so I could extract from there some patterns. Other things that we could do is to say, okay, I capture the data in the wild, and from that data, I try to extract some kind of mixed model, and then I try to generate or extract this type of patterns. What I will be talking next in the next slide is that a good way to do this, and it's something that is something very interesting for us, is to use more, let's say, generative models to automatically do this. Let's say when you want to generate synthetic data by extracting or by analyzing some data, what you want to do at the end of the day is to learn the background distribution of that data, so that then you can, let's say, somehow understand what's going on or to reproduce what's going on in there. There is a whole field into machine learning that is very popular, that it's about generative models. And generative models, again, in a data-driven manner, what they try to do is to basically reconstruct the distribution probabilities of this complex, let's say, data that you might have in some kind of data-driven manner. So even though the whole model or the whole distribution would be something very, very difficult to actually detect or to identify, with these approaches, you can generate data that will be following that type of things that you are following or you are seeing. And with that, you can say, okay, I can build the normal operation profile of this network. I can then simulate different type of anomalies. And in those situations, I could then have sort of ground truth to see if my anomaly detection algorithms work fine or not. So yeah, this is something actually very powerful for us. Instead of having access to ground truth, what we try to do is to synthesize the ground truth in the best manner we can. Definitely. So we will be talking something
Thank
about
you.
this.
There's a long history of that in the phone business with circuit switching.
Exactly.
So
yes.
But it's essentially the same kind of problem, because it's driven by human behavior or by economic behavior or something like that. Society has certain rhythms.
Definitely. And yeah, this is something we will be talking about this. Good question.
Thank you.
Welcome. Okay, I mean, if we don't have more questions for the moment, I propose let's take a break of 5 minutes. So we come back at 5:10, and then we jump into some of the applications, and then we start getting a bit more into learning itself. So I will try to go slowly into the deep learning part, because I think that's interesting for everybody. But then I will show you that deep learning is already now not what we used to see 2 or 3 years ago. Okay? Okay, good. So see you in 5 minutes.